Hello everybody and welcome to the Team Grothendieck weekly status update. Today is Tuesday the 28th of February. It might be Pancake Tuesday where you are. It is here. So the phases that we are in currently, two ongoing phases, are the block synchronization and the EVM or transaction execution. We're rapidly approaching the end of block synchronization, and we're in pretty good shape with the with transaction execution as well. So I think we'll go straight into a demonstration. We have a demonstration today of our EVM. So over the last week, the two sets of tasks, I guess, that we've been working on. One is, as I say, some cleanup around block synchronization. So, for example, using persistent node keys and creating a distributable execution. And then on the other side, we had a significant bit of work to do on the EVM as regards integrating with the rest of the system. So while we had done some work on implementing the various opcodes, last week was really about integrating that with the rest of the system and some of the complexities that threw up in terms of creating accounts from within contracts and things like that. So Radek, you have a demo for us.
Yes, I do. Hello. Can you see my screen?
Yes, that's great.
Great. Okay, so today's demo is going to be about, well, you can see the plan in the right window. It's going to be about certain API changes, the API that allows the virtual machine to access the Ethereum world state, that is the accounts and their code and storages. And that was motivated by the need to implement the call instructions, the three instructions you can see here: call, call code, and delegate call. Then I'm going to present Solidity Code that takes advantage of those instructions. You can actually already see it on the left. Then I'm going to show you the new tool that was built for running EVM code in a mocked environment, the EVM runner. We'll sum up with some conclusions. Okay, so regarding the API changes, previously our contracts were quite simple. The set of instructions that we had implemented allowed for mostly stateless contracts to execute, like the Fibonacci sequence calculator that was shown previously. Actually, that one was updating storage, so it had some state, but that was a very naive implementation. It was changed in this iteration. So now we do have a single point of access to all the state that is needed by all the VM instructions, and we can call other accounts, create new accounts, and so on. So yeah, those, as I said before, those changes were required to implement call, call code, and delegate call. These three instructions are used for interacting with external accounts code. So let me try to explain the difference between them. The call instruction is what is known canonically as message call. A message call can be viewed as an internal transaction that occurs during the execution of code. It's not an actual transaction. It doesn't end up on the blockchain, but the results, the effects of applying it are pretty much the same. So, for example, when contract A calls contract B, the contract B's code will be executed in the context of account B. Means that whenever there's, for example, a change in the storage, when that code puts some value on storage, that will end up in accounts B storage. Also, if the call, if there is ether value passed with the call, then we will transfer that value from account A to account B. On the other hand, call code and delegate call instructions can be viewed simply as fetching the code of an external account, but executing it in the context of our own account. So for example, when account A does delegate call to account B, that account B's code is executed, and if it puts any values onto storage, then account A's storage will be updated. Also, no value transfer will be ever performed. The balances of those accounts will not be directly affected. Now, the differences between call code and delegate call are very subtle. To certain constants that are seen by the executing code, like addresses of caller and own address. And the important thing is that the delegate call instruction was added later as a remedy for certain quirks that call code has in regards to those constants. I'm not gonna go into the details here, it is beyond the scope of this demo, but interestingly, what has been the functionality that is implemented with Solidity that previously relied on call code is now compiles to delegate call instruction. It was so call code can be viewed as an obsolete instructions, and for that reason, I'm not going to mention it further. Okay, so now that we know about those instructions, let's look at the Solidity code on the left, and let's try to understand how it utilizes those instructions. Here we can see three contracts: a contract caller, which is going to call other contracts, the contract callee. We are going to call this with the regular call, the message call, and the library lib. Now, the difference in contract and a library is exactly that calls to library will be compiled to delegate call instruction, contrary to a regular contract, which will be called with a call instruction. Okay, so we have two useful functions on the caller here. So this one will call the address that is passed to it. Now, this here is an interesting bit. This is simply casting. We have some address here, and we cast it. We assume it is the address of the callee account. It doesn't have to be true, actually, but we assume that, and we call the function increment on it. Now, when we're calling the lib, we're simply calling the instruction of the lib. Now, how that works, since we don't know at this point what is the address of the account that holds the lib's code, I'm gonna come back to that later. But what's important for now is that if you look closely, those two contracts, the callee and lib, actually implement exactly the same functionality. Now, you may find it strange that I used assembly mode here. The reason is that libraries in Solidity cannot update storage. And it makes perfect sense because library doesn't know anything about the account that's going to execute its code. So any changes to storage are forbidden by Solidity language. But I can still circumvent that by using assembly mode and do some value storing. And the reason why I'm doing is that, of course, I want to show you that this code, in fact, runs in the different contexts. Another slight difference is that this function is payable, which means we can transfer some value while executing it. Library functions cannot be payable. It will make sense since there's never a value transfer when using delegate call. And yes, that's pretty much it about the code. Oh, by the way, if storage modification were allowed on library, that code would have looked simply like this. Okay, so at this point, are there any questions regarding this code?
Yeah, so Radek, the assembly that you've used in lib, it's not supposed to use any store statements because it doesn't have any knowledge of the account or the invocation it's running under. So how does that work then? When you use assembly?
It's not supposed to, in the sense that Solidity doesn't allow it, but EVM does.
Okay.
So it probably doesn't make much sense to do that, which is why Solidity forbids it. But theoretically you can. I'm not sure what would be the practical application of of doing so, but for this demo it is practical.
Okay.
Okay, so then let me move on to presenting the new runner tool. Well, actually, before that, let's compile the contract. So let me move here. So this is the file with the Solidity code, and well, I've done that before, so I'm just going to take a command from history and compile it. It's quite quick. Let's look at the results. We have new files here, the bin files for all three contracts, and the ABI files. They are simply JSONs that hold interfaces to those contracts. They list all the methods and their arguments and returns. It's a bit unfortunate, though, that the naming convention is different for those files, for bin and for ABI. It's practical for the EVM runner for those to be named the same. So I'm just going to fix that quickly. Okay, and now we can. Now we can almost run the EVM runner. Let me just show you one more interesting thing. That here we simply call lib increments without any address. So how does that work? Well, let's look at color bin. So these are simply bytes that represent the bytecode, and the interesting part is here. It's a placeholder for the address of the library. Once we've deployed our library, we can then get its real address and link it with this code. So let me do that just now. I'm gonna fire the EVM runner. By the way, the EVM runner is a Java file that is compiled from our etc client code. The EVM runner is part of our client, but it currently lives on a separate branch. Okay, and an interactive shell appears that will allow me to run some commands. I'm first gonna start with creating the lib. Okay. Okay, it got created, and we can see its address. Now, when creating contracts, the address is actually deterministic. So, so because of that, I can simply reuse the command from history you may notice that this address is the same as this one. So let me link that. And now let me show you that bin file again. You can see it no longer has a placeholder. And in fact, if I search for this, you can see it right here. So now I can continue with running the code, and I'm going to create the remaining accounts. Okay, that's calling. And for caller, you can notice that its constructor is payable, which means that I can, Solidity allows for it to be created with some initial balance. So I'm just going to pass 1000 way to it. Okay. And now we can look what accounts we have created. We have all those 3 accounts and a certain dummy account that was used to create those accounts. Now, if we look at some info about Collie, for example, we can see some information. For example, its balance is a zero, whereas the caller's balance is exactly 1000, like what we passed to it. Right. Now, let's have one more look at the creation of those accounts. You can see that as a result, there's quite a bunch of info output, some gas used, whether there was some error, some return. Creating a new account is actually invokes the virtual machine. Some codes are run on virtual machine. That's why some gas is used, and there's this weird return data. If you're interested what that return data is, please ask me at the end of the demo. It's not really that important, but it's interesting. Okay, let's. What else can we do with our? We can, for example, list functions of caller. We see call lib and call, and this is actually what that ABI file is used for. We can access the human readable names of the functions. What else can we do? We can, for example, we can view caller's storage. It's initialized with 0 value, but probably the most interesting thing is that we can view the caller's code. And this is simply the bytecode presented in a sort of human readable way. Well, the interesting bit is that we would expect to find exactly one delegate call instruction here. Yeah. And there also should be a one call instruction. Yeah, there it is. Caller is something else. Never mind. And never mind that weird thing at the end. Solidity compiler always puts some metadata at the end of the code. Okay, I think I've explained enough to actually start presenting some functions, some interactions between contracts. So caller will call. Hold that thought. Let me check the callie's address again. Okay, this is the address, and caller will call that address. Okay, so there is some gas used. The return value is 1. By the way, I may have not said that. Those functions that I implemented here simply take a value from storage, from a constant address, and put an incremented value back on it. And they also return the same value. So we would expect to see that the caller storage is remains the same, the 0, whereas Collie storage should be 1. Yes, and also as you can see, when we call increment on the Collie, we pass a constant value of one way. So Collie's balance should be increased to 1, and Collier's balance should be decreased. Exactly what we expect. So let me maybe just run that more times just to see what happens. 2, 3, 4. And as we would expect, Collie storage is updated. Collie storage remains the same. And the balances gets updated. Right, one more interesting thing is that the EVM runner enables us to specify gas to be used for the function call. If we don't provide this by default, it is maximum gas value. As we can see previously, gas used was 13,000. So if we're gonna pass only 1,000 to it, that should result in an out of gas exception. Exactly. If we, on the other hand, pass enough gas, that should be just fine. And by the way, I'm going to show you that we can also pass some value to it. Now, this value goes to the caller account. The value that gets transferred to Collie is not affected. It is hard coded here. So if we pass 100 to caller, we would expect the caller's balance to increase by 99 because it will use the 1 to call Collie. Yeah, gas used and balance was increased by 100, 99 actually, and Collie balance is simply 6. We called it 6 times. Okay, so let me now show you how that is different with calling a library. Okay, the library is statically linked, so we don't need to pass any arguments to it. Let me maybe first let me just show you that the lib storage is in fact empty. And now we're gonna call it. Okay, have the return 1. Its storage is still empty, but the caller's storage is changed to 1. And of course, no value transfer, no ether transfer occurs. The balance is as it was before. Okay, so let me just call it several more times just to make sure. 2, 3, 4, 5. And caller storage is 5. And lib storage is still empty. Okay, now just maybe as a question to you, not sure if you noticed, the gas calculation. You can see that for the first call to library, substantially higher. It was 22,000 for the first one and 7,000 for all the other ones. And it was actually similar with calling the contract. First it was 28,000, then for subsequent calls it was 13,000. So my question to you, anyone has any idea why that is?
Because with the first call we initialize the storage?
Exactly. Very good. Yeah. When its storage value changes from 0 to non-zero, that's storage initialization, and that costs more gas. Exactly 15,000 more. Okay, so that's pretty much what I wanted to show you.
And then Radek, so
yeah.
the following on calls just updated it, so there was no extra storage.
Yes. There was some price paid for updating the storage, but it was exactly 15,000 less than for the first time. Yeah, I'm doing the interactive to play with this. If not, let me jump to conclusions. So with this new API for interacting with the state of the accounts of Google Search, we are very close to completing instructions in the VM. There are two slightly more complicated instructions left.
Radek, if you can still hear us, it looks like your connection has dropped. Do you want to try reconnecting?
Yeah, can you hear me now?
I can hear you now, yeah.
Okay. So what was the last thing I said?
Yes,
I started talking about conclusions. So so I said that with this new API to interact with the state, with the external accounts, with their code, with storage, we are very close to completing the whole set of instructions implemented that need to be implemented in the EVM. There are two more, a bit more involved instructions left, which are create and self-destruct, but they are already in progress, and this new API should really help along with the implementation. Also, a bunch of new instructions were implemented just for the sake of those call instructions. They were mostly quite simple ones, but we're closer. So you may also wonder about this EVM runner, because obviously it didn't just appear overnight. So was it worth the effort just for this demo? Well, yes, because it's not just for the sake of this demo. This EVM runner was actually a proof of soundness of that new API. By implementing the a mock state, we were able to perform some manual testing and show that it in fact the new API meets our needs. Apart from that, it's also the mock implementation is a great Kickstarter for the actual real implementation that will use a persistent database. This mock state will be used in a library of contracts that will be used to test our EVM in more depth. Okay, so that's all for today from me, unless there are any questions.
I have just one question. What is the return data when you create the contract?
Very good question. So let me explain what actually happens when we want to create a new contract. Creating a new contract means creating a transaction with with an empty address, and that determines that the input data of that transaction is code to be executed during account creation. Now, this code isn't the same code that ends up in this account. The code that executes first is sort of an initialization. For example, it can initialize certain values in storage. It can create other contracts and so on. So, so yeah, we execute this code during initialization, and the return data of that code actually becomes the code of the contract. So this is the code. This is the code of the actual caller contract. It's not this. This is the initialization code, and this is the actual code that will end up in the account. And now, if I search for it here, you can see that it is a subsequence of that code. This code simply does some initialization, and then it copies part of itself as a result of execution, and that becomes the contracts code. Hope that answers this question.
Yes, it does. Thanks.
Okay. Anyone else have another question? No. Okay. Thanks, Radek. That was a very comprehensive demonstration and very interesting, and might even become a little bit of a reference for us going back, trying to explain some of this to ourselves. So thanks for that. Okay, so where does that leave us? I'm going to share the screen and just show where we are. In the plan. Okay, so I'm hoping you guys can see that. As we've said a couple of times already, this is the blockchain synchronization. We're approaching the end of that now. Here in the next week. I don't think you can actually see the. Yeah, you can see the dates now. So this should be sometime in over the next week, and then transaction execution is due as well. Now, as I've said before, this is including roughly about a week or 2 weeks of our reserve. So we do have a little leeway there. But starting tomorrow, we'll be looking at planning what it is we're going to do over the next week or so, sprint or so, to bring these to a conclusion and do a large demo of the whole blockchain synchronization. And eventually the transaction execution. I wouldn't expect that to be quite so soon. We may well we'll most likely divide them up into 2 areas. And then beyond that, there's the command and query interfaces, and finally new block creation is the 4th phase, which will start beyond that again. And just for anybody who's interested, this is published on our website under the Ethereum Classic project area. Okay, so that's last week. That's the demo, and that's what we're going to do over the next week and where we are in the phases. Does anyone have any other questions for us? No? Okay, well, in that case, I think we're done for this week. Thank you very much, Radek. That was an excellent demo, and talk to you guys tomorrow, and same time again next week. Bye-bye.
Bye. Thank you, everyone.
Bye.
Bye. Bye.
Very short and very precise meetings. Thanks.